In this video, I want to look at the basic theory of interpolation, what it is, and a few different types of interpolation. Often in animation, you'll have one set of state at one frame and then some set of state at some future frame, and some attributes you want to blend between the intermediate frames. For instance, take my pen. Here I have some rotation, some other rotation, and I want to blend between those angles. What I'm going to do, that's not so great, but here we have it. I'm going to define some sort of parameter, alpha, and say, well, when alpha is 0, some variable will take some value a, and when alpha is 1, the variable will take some different value b. Now, the height here is just to visually show that the value is changing. And then the question is, how do we get from one point to another point over that span? So the simplest way to do this is to be linear. So to draw a straight line directly, try to do this in one go. Pretend that's straight. Okay, so for linear interpolation, we have that the value v will be, well, 1 minus alpha times a plus alpha times b. So we can see that this is a straight line formula because the power of alpha is 1 at most, or 0, in all of these individual terms. And we can see that this is correct because when alpha is 0, we will have 1 times a plus nothing times b, so we are completely at the a value, and then when alpha is 1, we'll be completely at the b value because this bracket will disappear. Okay, and that's fine. But I will also mention, with these different paths that we want to take from one value to another value, typically I would want them to be monotone functions. That is, they're always increasing. In this case, they could always be decreasing, that's fine as well. But the reason I don't want a non-monotone function is if we visualize my pen going from this angle to this angle, if we're increasing them, we're always going towards the target angle. But if we have a section of decrease, then we'll go up, 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 back a bit, and then continue. I mean, that might be what you're after. It's not for me in this case. So the really cool thing about interpolating the alpha parameter between 0 and 1 is 0 and 1 are very nice numbers. If I multiply 0 by 0, it's still 0. If I multiply 0 by 1, it's still 1. And so what we could do is, instead of taking these brackets, we could square all of that and give a sort of parabolic path, which goes the same way. So in the quadratic case, we'll have v equals 1 minus alpha squared times a plus alpha squared times b. And the same edge cases apply. So when alpha equals 0, we've still got 1 times a. When alpha equals 1, we've still got 1 times b. But the difference here is that if we look at the slope of the line, if I drew this more exaggerated, it would look a little bit like this. So as we go towards b, the slope actually increases. So this is what we call ease-in animation or interpolation, because at the beginning we're going very slowly, we're easing into the motion, but then as time goes on we speed up. So my pen would be going, very slowly, and then whoop, like that. Increase the power, and that effect is pronounced, but it always does the same thing. Now, the inverse of that is ease out animation, and this is sort of something like this. We want the interpolation to go very fast and then slow down. Very fast and then slow down. So an example of this would be the square root. But I'm just giving canonical examples. If you want to pronounce this, just keep dialing up the powers. So instead of taking the square root, take the 4th root, the 8th root. Take the 15th root, it doesn't matter. What you'll be doing is just exaggerating this. So if we were to take a higher root, the initial change would be faster, and then it would sort of asymptote well, it would asymptote towards the same end value. So the reason that the quadratic sort of squashes it downwards is that when you raise a number to a power, any number less than 1 becomes smaller. So 0.5 times 0.5 makes 0.25, which is even smaller. So it's penalizing numbers which aren't 1. On the other hand, the square root is sort of rewarding numbers which aren't 1. Or between 0 and 1, you know what I mean, because it's doing the opposite of the square root. Now, this is all well and good, but what if we want to do something really funky? So remember, alpha is just a parameter that varies between 0 and 1. We do not need to use polynomial interpolation. Okay, so that's fine. The next question is, can we build an interpolation which looks a little more natural? Isn't too weird, looks natural, has an ease out, ease in, I guess. And the answer is, yeah, for sure. One example is the sine function. So if we have a circle, sine is more or less the y-coordinate of the point on the circle at every angle. It sort of looks like this, or something. This isn't by any means a good drawing, but the point that I'm getting at is I want to capture this region of the sine function, and I want to map that onto my interpolation parameters. So for one thing, we say, like, at which angles do these occur? Well, we know that we have the maximum height when theta equals 90 degrees, or in radians that would be pi on 2. And we know that we have the minimum height when we have negative 90 degrees, or negative pi on 2. Okay, so one thing we should do is we can take sort of, what do I have here? Okay, I'll just, I'm thinking out aloud to myself. So here's my little half period of the sine function, and this is sine of pi on 2 times alpha, but then, yeah, no, it's pi on 2 times alpha. Because then when alpha is negative 1, we're down here. When alpha is 1, we're over here. Great. But that's not quite what we want, because then we want to map that. We want to map that over to the 0 to 1 range. Again, a little tricky, but I'll just give the short answer. So what we can do is we can go, first up, subtract 1/2 from alpha, and then multiply that whole thing by pi. So when alpha is 0, we have 0 minus 1/2, that's negative 1/2 pi, gives us our minimum. When pi is 1, we have 1 minus 1/2, that's positive 1/2 pi, gives us our maximum. So now we've sort of squashed it into this range, something like that. And now what I want to do is shift it up. So what we can do is just add 1 to that, get our minimum, come up, have our maximum, and then divide all that, because if we add 1, we would be going from 0 to 2, halve everything, we're now going from 0 to 1, as expected. Okay, so what I'll do is I'll define a new parameter, call it beta, that's what it's equal to, and then our interpolation will be the value is 1 minus beta times A plus beta times B. And there we have it. So enough theory, let's have a little look at the code. Alrighty, here we are in the code, and I actually went ahead and coded this up ahead of time, but I'm going to talk through it. So at the moment, this is just demonstrating linear interpolation on these two legs, these bones. Yep, looks great. They're walking. And the thing to bear in mind, by the way, I should have mentioned this before, by no means do we need to do anything other than linear interpolation. I use linear interpolation in all of my stuff. It looks fine. I'm happy with it. But I do think just seeing a few different rules gives a good understanding. Anyway, so the thing to bear in mind is that this motion is very even. It's very uniform. Now, in contrast, we can, let's look at interpolating quadratically. So it's the same thing, but all we're doing is we're raising these coefficients to the power of 2. We're squaring the coefficients in the combination. Okay, so let's have a look at that. What we can see is sort of very slow, and then whoop, it's like an ease in. Something like that. This is sort of a weird way to walk, but I guess some people are into that. Okay, so remember with the interpolate quadratic, it's sort of ease in. Now, interpolate square root is sort of ease out. So we'll have a look at that. And you may notice that it is a little hard to tell the difference between these two animations. Reason being that both the animations are looping. So the big thing to bear in mind is that both the quadratic and the square root interpolation are non-uniform. They have parts where they're slow and parts where they're fast. Okay, so let's have a look finally at the sine. And now hopefully, as you can see here, apologies for the background noise, but here we have it. Stuff that noise. So we take the sine, we have the same formula as before, so pi times this bit with the horizontal shift applied. Add on that 1 to get us from -1 to 0, halve the whole thing, and there's our interpolation. So what does this look like? Well, let's give it a go. And as you can see, at both of the extremums, we're easing. We're easing out, we're easing in. The legs are going slow at the extremums, but in the intermediate point, that's the fastest point of motion. This is basically simple harmonic motion on the legs. So there we have it. It's been some examples of interpolation, and I hope that you're feeling confident with that and ready to get out there and have some fun. All right, well, as always, have a great one, and I'll see you again soon. Bye.